Hey everyone, and welcome. So today, we're going to pull back the curtain on model evaluation. We all love to see that high accuracy score, right? But what does that number really tell us about how our model is going to perform out in the wild? We're going to go way beyond the leaderboard to really understand the deeper questions that proper evaluation can help us answer.
All right, so here's our game plan. We'll kick things off by looking at a super common trap with scoreboards, and then we'll break down the core idea of a holdout test. From there, we'll dig into what cross-validation is actually estimating before we dive into the messy reality of structured data. We'll wrap it all up by seeing how this helps us ask and answer way better questions about our models. Okay, so let's start with a scene I'm sure you're familiar with. You've trained, a dozen different models, you run your tests, and bam, one of them comes out on top with the absolute best score. It's so tempting to just declare victory and call it a day, right? Well, here's the catch. This is where you can fall into a statistical trap called the winner's curse. See, when you test a whole bunch of models and just pick the best one, that top score is almost always an overestimation of its real performance. The very act of choosing the winner introduces this optimistic bias, even if each individual test was perfectly fair. So how do we get around this trap? To really understand what's going on, we have to go back to basics, back to the absolute first principle of evaluation. And that fundamental building block is the simple holdout test. We can take this really simple idea and formalize it into something called a holdout utility. But here's the really crucial shift in thinking. A holdout test isn't just about evaluating one final model. It's actually a tool for evaluating the entire learning algorithm. The whole recipe that produces the model in the first place. Now, I know, math on a slide, but don't let the symbols freak you out. All this equation is really saying is that the final performance of our algorithm, that's GA, is just the score of a model, H, on our test data. And that model H is just what our algorithm A built from the training data. It's just a formal way of writing down that classic train-then-test process. And this is a really great way to think about it. You've basically got two layers at play here. You have an inner utility, which is whatever specific metric you care about. Could be accuracy, F1 score, you name it. And then there's the outer utility, which is the whole shebang. Take some training data, build a model, and then apply that inner metric on your test data. So a single holdout test is a good start, but it can be pretty sensitive to that one particular data split. And that, of course, brings us to cross-validation, a method most of us use all the time. But when you run, say, k-fold cross-validation and you average those scores, what is that final number actually telling you? What you're really trying to do is get a handle on this abstract concept called the estimand. You can think of it as the true kind of God's eye view of your algorithm's performance. It's average skill calculated over every single conceivable train test split that could ever be drawn from your data's underlying distribution. It's the ideal theoretical target. Now, in a perfect world, if you wanted to calculate this estimand exactly, you'd use something called a U statistic. This would mean taking your sample data and averaging that holdout utility over every single possible permutation of train and test sets. It's the most accurate, unbiased estimator you can possibly get, but for any real data set, it's just completely computationally impossible. And that, right there, brings us to the punchline. Cross-validation is our real-world compromise. It's what's formally known as an incomplete U statistic. So instead of trying to calculate every single split under the sun, it just samples a handful of them, what we call our folds. It's still a totally unbiased way to estimate performance, but it's a practical approximation that will actually finish running in our lifetime. Okay, so this whole framework of holdouts and cross-validation is super elegant, and this is a big but, it all rests on one giant assumption, that our data is IID, meaning every data point is independent and identically distributed. And let's be honest, in the real world, that's often a total fantasy. So this means we need to make a really critical distinction. Standard cross-validation, that's for measuring general performance, and it assumes any data point is as likely as any other. But what if we need to measure conditional performance? This is what we turn to when our data has some kind of structure or dependencies, or maybe when we just have a much more specific, targeted question we need to answer. And this is where we get some incredibly powerful tools, like off-training set, or OTS, evaluation. OTS lets us put a formal restriction on our holdout utility. We can specifically ask things like, how well does my algorithm perform on data where the inputs, or maybe the outputs, are fundamentally new and were never ever part of the training set? Look, this isn't just theory. Let's make this real. We're going to look at two practical examples to see how we can use this idea of conditional performance to answer much more precise and, frankly, much more useful questions.
So first, imagine a chemistry problem. Let's say we're trying to predict metal ion concentrations in drinking water. But because of how the experiment was set up, we have a ton of repeat measurements for just a few specific concentration levels.
You can see here the outputs are definitely not independent. The same values pop up again and again. Now, if we use standard cross-validation, the model could get a really high score just by memorizing these common outputs, which is totally misleading. An OTS output evaluation forces a much better question. How well can this model predict for a concentration level it has never seen before? That's what we really care about.
Okay, now let's pivot to a totally different kind of problem, a spatial problem. Let's say we have some geological survey data, but it's all clustered in one specific region. The most important question isn't how well it performs on a held-out point inside that same cluster. No, it's how well it's going to generalize to a location that's miles and miles away.
And the solution here is just as intuitive: spatial cross-validation. We just add a condition to our holdout split. We simply require that any test point must be a minimum distance, we can call it delta, away from all the points in the training set. This directly tests the model's ability to extrapolate, and it answers the exact geographical question we care about.
So, after all this theory, after all these examples, what is the big idea here? What is the one thing you should really take away from all this?
It really all boils down to this. Choosing an evaluation method isn't just some technical detail you pick from a library. Your choice of evaluation method, whether it's standard CV or OTS or spatial CV, is the precise definition of the scientific or the business question that you are trying to answer.
So let's recap real quick. Standard cross-validation is your go-to ruler for measuring general performance, but it assumes your data is all neat and tidy. When reality gets messy, these conditional methods like OTS or spatial validation become your specialized tools. They let you ask much sharper, more practical questions. At the end of the day, how you choose to measure is how you're defining your problem. So I'll just leave you with this thought. The next time you're about to run your evaluation script, just pause for a second and ask yourself, what is the exact question I am trying to answer here? Don't just ask, how good is my model? Instead, ask, how good is my model at doing the specific, challenging, and important thing that I actually need it to do? I promise you, the answer you get will be far more valuable.